All right, I think we're live. Hi, everyone. Thank you so much for joining this session. I'm going to give a couple minutes here for folks to join. I can see people joining in. So I'll just give a couple minutes, like a minute or so, and then we can get started. I'll introduce the session and take it from there. Right. Let us know where you're joining in from today, and if or you already know XTable, or if you're learning more about XTable and what this is all about in the Lakehouse world, let us know in the comments. Right, I see. Yep. Again, I'm joining from Toronto, Canada today, and yeah, this new series should be a good opportunity for people to learn more about the overall Lakehouse architecture in a way. So I think without further ado, we can get started as people join in. And also, this is a recorded version, so we will have this session as part of our YouTube channel, which I'm going to share later in the LinkedIn page as well. All right, so why are we here? Basically, this is a new series about pretty much around XTable, Apache XTable, what the project brings. It's open source projects under Apache Foundation. And we have been talking a little bit about this for about a year or so now, like, yeah, right? And we also have seen some good adoption stories about XTable, which is also the focus of this particular series that we want to bring it out to our users, to data engineers, data architects who are looking to build things around with different metadata table formats like Iceberg, Hoodie, Delta Lake, right? So that is kind of the focus, and overall the idea is that we want to bring value to the community. We want to make sure the community understands what we are kind of building with XTable. Maybe if you're interested to even contribute to an open source project, this is a good one that allows you to learn more about all the three different table formats, but also more on the storage part and how can you optimize things and whatnot, right? So that is kind of the focus. We'll also take this opportunity, like I said, to talk a little bit more about the nuances about the different table formats, right? We talk about like, a lot of times in the community questions comes up like how, a particular table format differs from the others. So I think this is a good opportunity. It brings everything together, and that's the kind of motivation. All right. So my name is Dipankar. I'm a staff developer advocate at OneHouse.ai. I focus on open source projects. As part of my jobs, have been doing that for some time now in the previous jobs as well. And I contribute to Apache Hoodie right now, Apache Iceberg. I used to contribute that in the past couple of years. Apache Arrow is a in-memory system that I used to work on the community side. And with Apache XTable, again, I'm leading this development efforts for XTable and making sure community and the people, the data engineers and the data architects and software engineers, they understand the value of something like this. So I'll be your host, and most of the time, and speaker at times like this one. So yeah, we'll take this opportunity to go towards that. So in terms of the agenda, what I'm thinking of today to start the series off, I'm going to start with some of the basics of the Lakehouse architecture, right? And when I say basics, before even going to the point of why we need something like XTable or interoperability, which is the kind of the broader subject, I thought like maybe it's a good idea to give some idea on the foundation of Lakehouse architecture, and then we'll go a little bit deeper on XTable, the problem and the solution, and then finally, talk a little bit more about the architecture aspect. So if you're someone who likes to understand like the technical bits and bytes, right? That's something to be considered as well. So basically, over the years, organizations have been kind of investing heavily on building centralized, reliable, and scalable data platform, right? So the whole idea was that if you could democratize data, right? And when I say democratize data, it means like letting more consumers in your organization, like data analysts, data scientists, they want to use the data, right, to further run their analytical workloads like BI, machine learning. These are very common use cases. So if you are, that's kind of the whole idea, right? The organizers want to make sure, as a data engineering team, data platform team, you want to make sure the data is available. So the data warehouses or data, OLAP databases, as I like to call them, were kind of the first one that enabled to deal with this. But then they lack the abilities to deal with unstructured data at that point of time, right? And even now, like, although we see a lot of data warehouses like focusing on, unstructured data use cases, still the support is not that strong, and that kind of was the motivation before, right? So then with the data warehouses, we were able to get some, data into a central repository, which is great for BI kind of use cases. But then, with the advance of, like, tasks like machine learning, more advanced use cases with structured and unstructured data, semi-structured data, came the era of data lakes, right, with the Hadoop ecosystem. So with Hadoop ecosystem, what basically happened is that, we were able to, write the data files, as immutable data files. Like Parquet, for example, is one of the most common one. And we were able to, like, leave that in a data lake environment, and let our data scientists, like, consume those Parquet files, or do some analytics on top of that. But the problem was that, you can't just dump all of your data in a data lake and let your analyst or scientist, deal with the physically stored data, right? So if you still wanted to do something like business intelligence with BI reporting and stuff, you still needed to organize the data and get it out in a structured form, right, to a data warehouse. And then again, you have to do your reporting on top of that. So it's kind of a two-tier approach, right? We still have a data lake, we still have a data warehouse. We have some of the data in our data lake. We want to, like, take a subset of that, build a reporting on top of that. That's kind of the most common use cases. And that's the problem, because you're running two different architectures, two different environments, which is cost intensive. It requires engineering efforts and whatnot, right? And the most important thing that kind of data lake lacked, was those atomicity and consistency guarantees with transaction, right? So things such as update, deletes, right? You cannot do ACID-based transaction on a data lake. And when I say cannot, things like concurrent writes is the problem, right? Two writers writing at the same time at the same table, it's going to be it's going to be hard to have those reliability guarantees. And most importantly, it was getting really hard to make sense of all of the data, right? Because there is no real governance or data quality checks on the data that was being dumped on the data lake, right? And we call those data lake kind of like data swamps, in the industrial term. But the whole idea is that, how can you even build a machine learning model around such data, or even like a, BI report around that data, when you don't have those quality controls in place, right? So these problems, they gave rise to kind of a new architecture, which is the Lakehouse platform on Lakehouse architecture, and that's kind of the idea where we are now, right? So what is a lakehouse, right? And before we even go to the fundamentals of it, you can guess from the name in a way that it's a combination of a data lake and a data warehouse. And when I say, like, it's a combination of the data lake and a data warehouse, of course it's not just combining the two architectures in a way, but it's basically bringing the best of both, like, the architecture, right? For example, data warehouses, they have great data management capabilities, right, and optimization capabilities, like things like compaction, clustering, ability to do things ACID-based transactions, right, and time traveling, schema evolution. So these are some of the important things that we have kind of transactionally achieved in a data warehouse, right? Whereas in a data lake, we don't have those things, right? And that's why kind of like we are thinking about this kind of architecture now. Whereas data lake, on the other side, they are the ones that provide scalability, right? Especially with now with, like, the cloud object stores like S3, Azure or Google Cloud. Um, these object stores allow you to scale infinitely, right? And kind of from a cost perspective, also they are really amazing, right? They provide, like, comparatively cheaper prices compared to this kind of incumbent, like, data warehouse storage, where there is a money to store the data and all those things. So Lakehouse basically builds on that idea, right? And the most important thing that kind of ultimately lays the foundation for a Lakehouse is this kind of transactional layer, if you see in this image, right? That comprises of the table format, the metadata itself, different kind of, like, techniques, which is like native to data warehouses and databases, like concurrency control mechanisms, transaction log, and this kind of thing, right? So let's talk a little bit about the various components that are involved in a lakehouse, just to give a quick idea. So we'll start from the bottom part and move to the top part. As you see, it's kind of a bottom to top approach. So we have the cloud storage, the data lake storage on the extreme bottom part, right? And this is where your data lands after ingestion from operational systems. What kind of pipelines that you have, right? So Amazon S3, Azure Blob, like I said, Google Cloud, all the major vendors, they support storing any type of data, right? Whether it's structured, semi-structured, doesn't really matter. And they also provide the required performance and security perspective, right? And then we have the file format on top of that, right? This is where the actual data is stored, right? And usually in columnar formats. Of course, there's an advantage towards storing data in columnar way for analytical use cases, right? Mostly read-heavy workloads. So, Apache Parquet, ORC are the common one, but also, there are some read-heavy workload-focused things like Avro, which is still used, and, for specific use cases. Now, like I said, one of the most important component that makes up the Lakehouse itself is basically the table format component we have been talking about. But overall, like the transaction layer adds to that, right? It's not just the table format. So if I have to kind of generically talk about what a table format does, right? And this thing, it confuses people, right? So basically, a table format is kind of an abstraction, right, on the physical data structure's complexity, right? So what I mean to say is that, and we will talk a little bit more in depth as well, is that we have the native Parquet file, right? The data files itself, right? So these files need some kind of a schema to be managed, right? And to be able to achieve this transaction on top of this Parquet file. And that's what the table format brings. So Apache Hudi, Apache Iceberg, and Delta Lake are kind of the three popular table formats, right? And they have widely gained enterprise adoption. But in the past, of course, we have had one common table format, which is the Hive table format as well. And if you move a layer on top of that, which is the kind of the compute layers and the downstream applications like the BI tools, the machine learning frameworks, everything comes on top of that, right? And the whole idea is basically with this Lakehouse architecture is that you keep your data part, which is your table format, your file format, and your transactional layer pretty much open, right, as an independent open tier. So that means you can bring any kind of compute that kind of supports that particular table format or file format to work with that data, right? So the perspective I'm trying to bring here is basically that in the previous world, like with data warehouses, like closed data warehouses, right, you would have this similar components, right? This file format, this table format, this transactional layer is pretty much the same, right, in a data warehouse architecture. But the difference being here is that with the data lakehouse, like I said, the data itself is open. The file format, the table format, the transactional layer is itself open, which allows you to be more independent about the compute, right? And you are not locked into a particular vendor system and have to rely on their compute engine, right? So this is the kind of the main thing like we are talking about with the Lakehouse architecture. And one important aspect to mention here is, of course, that we are also seeing a lot of data warehouses now kind of like changing their needs as per the customers, right? So now we have like data warehouse vendors. They support different open table formats as well, right? Whether it's Hudi, Iceberg, Delta Lake, right? So that means that you are giving customers or users more ability to control of their data. In reality, it's not like it's completely open in a way. There's still kind of a control in terms of like the catalog and those kind of aspects. But at least our like the ability to for our customers to like store data openly versus like storing in like proprietary storage has kind of reduced, or we can like kind of see that trend in terms of like reducing that focus. All right. So if we are interested to learn a little bit more about this table formats and like data lakehouse architecture, I highly recommend like reading the data lakehouse paper by Databricks. They started like this concept in a way. But also I also published a paper back in my previous job where I kind of do this comparison with the data warehouse and a data lake and try to understand like from my perspective like what this lakehouse architecture brings. All right. So coming to our focus now, which is our table format, right? So we have talked a little bit about like how the table format provides the abstraction, right? So is this table format something new, right? I mean, to answer that, I mean, no, not really. I mean, maybe the jargon or the concept, it's kind of like sold as something new, whereas it's not, right? So usually with databases, we have seen the concept of tables. Of course, it's not a new concept, right? So these table formats are what loosely databases have been referring to as storage format for years, right? And companies like Oracle, Microsoft, they have been doing this with relational databases for years now, right? So basically, it's a way to organize a data set file to present them as a single table, right? So users don't have to really know about the physical bytes and files, and they can just have that abstraction on top of that, right? And in the past, database vendors have had their own storage engine handling the data files on the disk, and the compute engine, like I said, it's kind of closed, one particular system. So they have their own compute engine, own storage engine, and they are dealing with those data that is stored in the storage itself. Now, in the big data world with Hadoop and HDFS, we ultimately ended up with Hive, right? So more people can have access to data. But also there was a need to define a schema, like I talked about, right? So users or engineers can, interact with that. And that kind of gave rise to the Hive table format. So basically, Hive allowed you to, data analysts, for example, they can use something like Hive query language, which is similar to SQL, and provide the semantics like SQL. So you can basically interact with the data that was present in a data lake, right? Versus writing MapReduce algorithm, which is like limited to a particular set of engineering folks, right? So with Hive, here's just an example. Of course, I wanted to show what basically a table format does. Is that with Hive we have a table in a data, a particular database, and it's composed of one or more directories, right? You can see these directories, and here you can see just one directory, of course, in the image, but each particular directory will contain those immutable data files, right? Those data files. So that's kind of the idea, right? And the idea is that you also track some of the statistical information, some of the metadata information that allows you to run more efficient operations versus every time interacting with the data files. Now, coming to our modern day table formats, right? Iceberg, Hoodie, and Delta Lake, right? I mentioned that a little bit more. Some of you may already be aware of these formats, but for folks who are new to this space, let's kind of take a quick bird eye view and understand how these kind of technical fundamentals make an impact on a data platform, right? So if I have to give you a one-liner of what these all three formats are, these are basically metadata abstraction of data files on object storage, right? How the metadata files are organized and designed are a bit different for all of these three table formats, but the overall goal is the same, right? Ultimately our goal is that we want to be able to track metadata related information and provide that schema on top of the native file format. So Delta Lake does this with a JSON-based transaction log. Iceberg uses a bunch of metadata files, manifest files, and Hoodie kind of takes a timeline and indexing-based approach, right? So you see how the structure is kind of designed in a different way, but ultimately the goal of all these formats is basically to provide ACID-based transactions, schema evolution, time travel, and all these kind of use cases that you run on top of that. So once you create a metadata abstraction on the files on storage, now you have your ability to explore some of the foundational characteristics like table and SQL type semantics, which is very common, like I said, in a data warehouse. And because these data files on the storage are immutable by nature, right? Having that metadata layer on top allows you to do those ACID-based transaction. And of course, we are going to talk a little bit more about the statistical file. Basically, individual Parquet file, they have their own footer, they have their own metadata, right, about the column level stats or row group statistics and those kind of things. So these table format, they basically gather those information and they maintain it in the table format. So that can be used for pruning and predicate push down and those kind of optimization techniques versus opening each and every Parquet file and reading from them and closing them, which is very IO intensive, and it can be a lot of cost wise, it can be a lot at scale. So coming to the main point, the thing is fundamentally these three table formats are not much different, right? So when the data is written to, and I can show that how, when the data is written to a distributed file system, right, S3 bucket or whatever it is, these three formats have similar structure, right? So going a little bit inside of what particular thing actually comprises this table format, right? So these are basically the 5 things that you might take away. These are the things that are basically forming the table format. So one is the schema information, right? It describes the structure of the table, the column names, the data types, nested structures and whatnot, right? This kind of information. Partition related information, right? You want to get the, for example, the specific value or ranges of values for each partition. So that way you don't have to look for every data file in every partition. You can do things like partition pruning and stuff. Statistical information, I talked a little bit more about that, the minimum and the maximum values for each column based on the Parquet file, right? And this helps in query optimization, and predicate push down and those kind of things. Of course, we want to keep a tag about the commit history, the transaction logs, what has happened in the table, what changes have happened. If 2 writers are writing at the same time, what kind of mechanism or techniques we are involving, to control that, right? So that the write happen in a successful state and doesn't end up with partial writes, or kind of like unexpected data. And that basically comprises the entire table format structure, right? If I have to like just break down the entire table format thing, these are the kind of 5 components you typically see. So that brings us kind of to the question of the hour, right? uh, oh, I hope I can see a comment that the video is frozen. Okay, I hope, Shahib, you were able to like see the video now. I see that working on my end. All right, so that brings us kind of to the tougher questions, right? How do we particularly select a particular table format, right? And what formats should I choose? And this is probably one of the most common question that I typically see being asked in a lot of like community conferences, or implementation things, helping customers in production and those kind of things, right? And to be honest, this is a tough question, right? Everyone's workload, use cases, ecosystem, they are a bit different, right? And there are so many factors to consider. So it is really a difficult thing to compare and choose one format, right, that really solves all of the problem, right? But overall, what it comes down to is things like feature level comparison, right? We try to compare like if a particular feature that I'm looking for is existent in this particular format versus the other one. If it is existent, how complex it is, right, to implement that, right? Or how easy it is to like adopt that. Are there any kind of additional advantage by adopting that particular feature, right? Then there is the complexity of implementation itself, right? For example, how tough today would it be to like to take one of this format versus the other and implement it, considering that I'm let's say a startup who's basically have a limited set of engineers now, or maybe you want to go with something like a managed services, right? There are different companies or vendors who are also providing managed services around this table format. So maybe that's your go, right? And overall, ultimately, two other aspects is that the ecosystem support, the query engine support, obviously, table format by themselves, they are storage layer, right? They are the storage part. But there is a compute engine side of it, which is super important, right? And that part is also like bringing the value here in your decision, right? Okay, let's say I'm going with X compute engine that allows me to like achieve my ETL pipelines, right? But does X works with Iceberg? Does X work with Hoodie? Or that kind of comparisons, right? And the other factor, of course, is also another important thing is the community aspect, right? All of these table formats are open source projects, right? So how these open source projects are being motivated and how the community is making a decision, it's important to take that into consideration, right? Is it just one organization making a decision for that particular format? Is it a diverse set of contributors who are making decisions around the particular formats, particular features, the value that they bring? So what I mean to say is that these different factors come into the picture when you're talking about this kind of decision to select a particular format. On top of these incumbent kind of like factors, right, there are also some new challenges as we learn from experiences of operating lakehouses in production, right? For example, newer workloads in a lakehouse architecture, we have seen with customers, they involve using multiple table formats, right? There are bigger organizations sometimes, or even smaller organizations, right, who started with a particular table format, right? And they kind of thought that that would work well for all of their use cases, right? But then now they realize that they have to rely on something else, right? So how do these different table formats they talk to each other within an organization, right? You cannot every time do a migration strategy. It's super tough to do that, right? It involves a lot of engineering efforts, cost factors is there, and overall it's a cumbersome strategy, right? Even if you are able to do like a one-time translation, like imagine like let's say you are able to like do a one-time translation, what happens for the next set of updates, right? Are you going to like be able to run something incrementally? Are you able to like run something in a more like cadence fashion where you are able to like get this right into the new formats? So these are some of the questions that you might want to like ask yourself when you're deciding on a particular table format. So the question really is, right, do we have to choose, right, or is there any another way, right? um, Usually when I kind of pose the question around using multiple table format, people ask, right, how do I do that? Like how do I like still use multiple table formats? How do I make them interoperable, right? Or do I even need to do that? So what it comes down basically is to with the overall Lakehouse paradigm is that organizations want to be more interoperable, right? And have that flexibility to choose any compute that they want, that is existed today, or maybe it's not exists today, right? You want to be able to take something that comes up in the future, which is really performant maybe for your use case, and you want to be able to use that with this different table formats, right? So ultimately, what it comes down to is basically like, if I am going with the idea of keeping my data open, how can I make this data open and interoperable between these different table formats? And just to show some examples here, from the real world, what we have seen from users, wanting to do something like this and more interoperable is that, these are just some basic examples. For example, like, a lot of the customers, let's say they are on like, Hoodie with EMR. Hoodie is great with like mutable, low latency based workloads. On the right side, they're really good, right? And provide some really faster ingestion possibilities, right? So maybe you're using Hoodie with EMR, right? But on the read side, maybe you want to use, your other team or like the same team using Snowflake, which supports Iceberg today and doesn't work with like Hoodie. So how do you make these different like tools and different formats talk to each other, right? And like I said, migration is not an answer here. Like in a lot of migration is totally not an answer at this point of time. And imagine the scale, right? The scale we are dealing with. Similarly, like let's say you're starting with something like Delta Lake with like let's say Databricks or Fabric ecosystem. It's easy to get started out of the box like with a managed service. But maybe on the read side you're using like something like Hoodie with Dataproc, right? With Spark. So how do you target these different aspects? And these are some of the like budding concerns we have found from the industry like implementations, right? This is what we kind of saw and like why the whole idea of XTable came into that picture. All right. So we are almost like 30 minutes in this particular session, and I want to like divert a little bit of focus towards now the solution now, right? We talked a little bit about the problem. So introducing XTable, XTable, like I said, is an open source project. It's incubating right now under Apache Software Foundation. That allows us to be more open. I know it's independent of all these different Iceberg, Hoodie, Delta Lake, just 3 different projects. But we, of course, have invited members from these 3 different communities to be a part of this new project, and also happy to have a lot of people like contribute to this at this point of time from these different like table formats and the Lakehouse space. So the idea behind XTable is very simple, right? Data should be universal, right? Like I said, like with organizations who are dealing with these different large scale like data implementations, right? So it provides flexibility for teams to choose and cater to different use cases, right? You want to use Hoodie today for your fast writer performance, fast ingestion things. Maybe you want to use something else on the read side. It's up to you. You have the flexibility. You don't have to be married to a particular single format. And ultimately, the goal is that you write in your one particular format and query using compute that works the best for you. So a little bit of more context here, and going into the depth of it. So XTable provides omnidirectional interoperability among these different Lakehouse table format. So the term omnidirectional, right? And what that means, let's first address that. So omnidirectional means you are not limited to just one directional conversion, right? You initiate from one format, and you can go with any other format in any fashion, whether it's round robin, round trip, however you want, without the need to copy or rewrite your data. And that's the most important thing to understand from this part, right? We are not touching the data files at all. We are just building on the idea that this metadata table formats like Iceberg, Hoodie, and Delta Lake, like I said in the beginning of the presentation, they kind of gather the same information, right? Although like structure is different, but if you take an intersection of the elements, they are pretty much the same. So we take advantage, XTable take advantage of that idea and basically builds upon that, right? So XTable is not a new or separate format, right? Instead, it provides abstraction and tools that are designed to translate this metadata from one format to another and be more interoperable. So the overall goal with XTable is basically that you can start with any table format of your choice today, right? And if there is a specific requirement to switch to another one, depending on your various factors, like we discussed a little bit more about that today, you are free to do so, right? That's the best part about XTable. So all you have to do is basically select your source. You have to select your destination, and XTable will translate the metadata layer, which can be used for your requirement, right? So the data file, they remain untouched. Only the metadata translation happen here, right? And how it works is basically is the I'm going to talk a little bit more about the architecture in the next slide. But in a more technical sense or in a more applied sense, basically right now at this point of time, it's just a jar, right? But you can hook it into like different tools and different things, and that can give you this kind of like translation and interoperability perspectives. So going to the architecture part, and the reason I'm touching a little bit more on the architecture is because I want to like show the components that are helping build XTable, right? And how these components allows us to achieve this interoperability goal. So there are three main components here. One is the conversion source, one is the conversion target, and the third is the conversion logic, right? So the conversion source is basically our tables format specific module, and they are responsible for reading the source tables metadata, right? And they extract information like schema related information, transaction related information, partition related information, and basically they take that information and they translate into XTable's unified representation, which is an internal representation, right? So that's what basically the source conversion source does. On the other side of the spectrum, we have the conversion target, which are basically taking that internal representation that we collected, right, from our target format, source format, and you take the representation and you accurately map it to the target format's structure, right? For example, if you're using like source as iceberg, you take iceberg's partitioning info, iceberg schema information, and you basically like convert into like target format. Let's say you're using hoodie or delta, you just map it to that, right? And the final part, which is basically the whole like the central processing unit of XTable, right, is basically the conversion logic, right? This is kind of the heart of the XTable, and it orchestrates the entire translation process, right? It does things right, initializing components. How do you manage the source and the target, right? Those kind of thing, right? XTable allows you to do incremental based translation. So what I mean to say is that let's say you've started with like iceberg to hoodie translation, you do a commit to commit based like translation. XTable keeps a track of the state. Let's say you committed like to till like commit number 4, and a new commit has happened on commit number 5. So XTable allows you to basically take that into consideration and manage the state so that you don't have to like do a full translation of all the commits again, and you can just take the delta commit and commit, and write that to the target table format. So that is basically the overall architecture of XTable, and kind of how it like helps us like achieve those interoperability goals. So I'm going to like take a little bit of time here. The presentation is kind of over. Like that's kind of the whole idea today. Like in this one, we are not touching on the practical aspects, but I'm going to show a little bit more about like the documentation and how we can get started and how we can like follow some of the already existing articles and blogs and those kind of thing. But in the next session, what I'm thinking is basically like we will have a use case and we will see XTable in action, and we'll basically build on this particular episode and we'll see how this translation happens on the fly, right? So let's dive into the GitHub, the project. It's under incubator XTable right now. This is what you can like look for the code, the source code. We see a lot of diverse contributions in this code itself. We are also preparing kind of the new release that we are targeting with this XTable now. And in terms of the documentation, xtable.apache.org is something that is what should be followed, to follow all the docs and the blogs and all this that's going to get started. All right. So if you go to the documentation section, you can actually see the different, we have basically like created your the entire step-by-step guide. So what you can do is like you can create your first interoperable table. You can get started using like a particular table format. How do you like create a data set? How do you run the particular sync, right? I talked a little bit more about this. But in general, like the source config and the target config that you set basically happens through this YAML file. So you can see here the source format is iceberg. That means I want to take iceberg table format and I want to translate it into other ones. So the target is hoodie and delta. You can do it at the same time, but be a bit careful about like running multiple table formats, because depending on the type of like and size of the data, it can be a lot. But this is what you specify the target format. This is where you give your table base part. That means this is where your iceberg table is now, and you translate that, and then your table data part and the table name. So once you do that, you can basically, take a jar. This is the jar that we have right now, right? This bundle jar will allow you to do that translation, right? And like I said, we're going to see a little bit more about that in our next episode around that. But if you want to just take this step-by-step guide, this should be it. Like, you should be able to follow that without any hesitations. In terms of our other example, we have a Docker demo as well. If you want to just take that demo, I think there are like a lot of services like Presto, Hive Metastore, all those different things. The other part that I kind of didn't touch today with the Lakehouse architecture is the catalog part, and that's something that is also like super important, like to understand. So let's say you have translated an XTable based table, right? You translated from, let's say, iceberg to hoodie, but now you want to make that table available to a catalog like Unity or something like that, right? Or Polaris. So we also have like a guide to do that. Like you can sync to Unity catalog. There are some prerequisites, but it's pretty easy to like get started. And once you make that table available to Unity, you can bring your compute engine as you would want, like, and do your analytics on top of that. I have a blog that I kind of wrote in the beginning of like XTable, and XTable was initially called as Apache one table. So this is a blog that goes over some of the basic like ideas behind the interoperability, right? And I'm going to share this over here as well, along with the other details. So let me just put it over here. All right, so this will give you an idea of the overall idea behind XTable, how to even like, run things like, the translation that I talked about, like the example, the code example, and what you should expect, and those kind of things. So in terms of the community, we have a pretty good community right now. Like I said, it's a really diverse set of contributions. We have like 895 people like looking at it, like 144 forks, which means that's a really good momentum considering like how we have grown from a very nascent stage to at least this point of time. And I would really encourage, if you're interested like to contributing or being a part of the project, like to take a look at the repository. If you understand like the language perspective from a programming perspective, that could be a good idea to like get started overall as well. So that is pretty much that I had for this particular session. And this episode 1 should be a good guide into how we kind of make this discussion around these different table formats, and different like possibilities with interoperability. But feel free to ask any questions, and I hope in the next one we can go a little bit more deeper into how to actually implement these things and how to run these examples. And in the further ones, I'm hoping to see like some of the real world use cases as well. So that would be really great as well. So thank you so much for joining, and I'll give a couple of minutes to see if I have any questions, and I'll take it from there. All right, one question that I got is basically is how do we like, is there a way to like hook XTable into other like like other tools and platforms, right? So yes, in fact, Amazon actually had a blog, AWS MWAA, run Apache XTable. So this actually is a good blog as well, that allows you to show basically run XTable as part of an Airflow operator using MWAA. Again, you don't have to use MWAA, but you can use something like Airflow operator to do that. I'm actually working on a blog as well that should give a good idea around how you can plug in like this particular jar into different things, and that should help understand a little bit more as well. All right. I think that is all that we had. And like I said, this new series, the focus is that we are going to focus on, all these different projects and different open source projects in the Lakehouse space, the table format specifically, but a lot from the interoperability aspects and what is even the need for such something like this. So thank you so much for joining me today, and I'll hope to see you in the next one. Bye.